Okay, so welcome everybody once more to the official IAU G2 online conference series. This is about massive stars, and today is my real pleasure to introduce our next speaker, Daniel Pauli, who has recently moved to KU Leuven as a FW fellow. He's already our speaker number 15, and I can tell you that the new IAU G2 Commission is already working in selecting the next group of speakers for the winter speak season. So you will hear about this new bunch of people soon. Daniel is an early career astrophysicist working at the forefront of the studies of massive stars and binaries at low metallicity. He began his academic journey with a bachelor degree in physics at the University of Bonn in 2018. And following that, he continued his studies at the same university and obtained the master's degree in astrophysics in 2020 under the guidance of Norbert Langer. Then he moved, still in Germany, to the University of Potsdam to work under the supervision of leaders on his PhD thesis with the title Unraveling Massive Stars and Binary Physics in the nearby low-metallicity galaxy, the Small Magellanic Cloud, as a proxy for high-redshift galaxies. And this is the topic he will be telling us more today. He defended in August this year, and as I mentioned before, he has recently joined the Leuven team on massive stars. He's an specialist in spectroscopic analysis of an stellar evolution, and also an expert in the modern non-LT model stellar atmosphere power and the stellar evolution code MESA. He's been PI or co-PI of several observing campaigns, so it's good that he's combining theory, models, and observations. He's been leading or co-leading an observation with the BLT, the Hubble, or the James Webb Space Telescope. And then last but not least, I think it's also important to remark that he has already good expertise in undergraduate teaching, lecturing, and public outreach. So he's very kind of motivated and promising early career researchers in our community. So as I say, it's a real pleasure to give the floor to you, Daniel. So whenever you want, you can tell us about your exciting science.
Yeah, thank you very much for the very nice introduction. I hope I can keep up with my talk. So as you see, the title is very long. So let's start with why massive stars, and especially binaries are important. So if we are in a galaxy, we have like molecular clouds, they collapse and they form massive stars and low-mass stars. And these massive stars only live a few million years, which means they influence their surrounding on an astronomically short time scale, especially when considering like the evolution of a galaxy. And most of the time, these stars are hot and appear as OB spectral types. They emit copious amounts of hydrogen ionizing radiation with which they can like shape their environment, stop and trigger star formation. And furthermore, these stars can evolve here. So as they evolve, they will expand, and single stars, they will appear as red supergiants. And during all of their life, they have strong stellar winds, which might shed off the hydrogen-rich layers, exposing the helium core and leading to the formation of helium stars or Wolf-Rayet stars, which also emit like copious amounts of helium and hydrogen ionizing radiation. And so if you have like a helium star and it has a strong wind, it's classified as Wolf-Rayet star. And during all of these evolutionary phases, these massive stars have like their strong stellar winds, which they deposit copious amounts of mechanical energy and heavy elements to their surroundings, and also enriching it like with metals. So, and in the end, these stars will explode as a supernova explosion, depositing even more energy into their surroundings. And all of this makes massive stars the main feedback agents in galaxies. But the question is now like, how does binarity change like this standard picture? So if you have two stars in a binary, at some point your initially more massive star will start expanding and will start interacting with its companion and transfer mass. And during this mass transfer, you remove efficiently the outer layers of these stars. And typically what is assumed that during a binary interaction, you just strip off your entire hydrogen-rich envelope and you form a helium star. But the big question is like, is this really true? Do you really lose the entire hydrogen-rich envelope or not? And if you assume that this is the case, that you always produce helium stars in binary interactions, then you might argue that binary products are actually the major sources of helium ionizing flux, as during stars which are formed in binary systems, they will always produce like this hot helium stars which can produce a helium ionization. Yeah. So I'm also talking about high redshift galaxies. So galaxies which were born like at the early cosmos, their light is redshifted, and this is a really nice measure of distance and time. So we can actually look back. But unfortunately, in these galaxies, even with the state-of-the-art telescopes like Hubble and James Webb, we cannot resolve the individual stars in these galaxies, but we get like an integrated spectrum, like I'm showing here on the left. And this integrated spectrum is the composite of the most luminous stars and contains valuable information about the conditions in the early universe. So as you can see, so I'm pointing also with the red arrows up here. I don't know if you can see my cursor well. This spectrum contains wind features like these P-Cygni profiles, which are associated with the spectra of the most massive stars. And to analyze these conditions, we need tools which can accurately model these spectra of these galaxies. However, the average metallicity in these galaxies that we are observing is quite lower, like a factor of 10 or even more lower than what we have in our own Milky Way, meaning that the properties and the evolution of these stars might be different than in our own galaxies. So and these properties of low metallicity massive stars are still poorly understood. But there's hope. So there's a Small Magellanic Cloud, which is an irregular dwarf galaxy. It has a low metallicity of 1/7 of solar metallicity, which is the same as a galaxy at redshift 2 to 5 would have. And it is actively forming stars. It hosts more than 1,000 massive OB-type stars, and it is also nearby, which means that we can resolve individual stars, study them, and conclude something about their evolution and their physics. So it is like the ideal environment to learn more about massive star and binary evolution, to see if we are doing stuff correctly and what this means for our interpretation of the spectra of high redshift galaxies. So the key questions I want to answer in this or to address in this talk are about binary evolution. So how do stars and binaries interact at low metallicity? So far, we just assume from our galactic knowledge that most of this binary interaction will strip off the full hydrogen-rich envelope. But is this consistent with observations of post-interaction binaries in the SMC? Furthermore, I want to know, like, what are the properties of this post-interaction binaries, and what does binarity do to a star's spectral appearance and also to its stellar winds? And what does this mean for our interpretation of the integrated spectra of high redshift galaxies? So to do this, I have done a big search for massive binaries in the SMC. To do this, I acquired like multi-epoch optical spectra from my own ESO program, but also like added some archival data to identify binaries and also like post-interaction binaries. But the optical data alone only tells you information about the stellar parameters, but nothing about the spectral wind and the UV, which is like this part which we see when we are looking at a redshifted galaxy. So I also acquired like UV data with HSD and also from like the Ulysses project to obtain like the stellar wind properties. But obtaining the data and identifying binaries is a nice part already. But to really understand the physics of them, you also need to model and understand the stellar properties. To do this, I used the power non-LTE stellar atmosphere code, which allows me to conduct a multi-wavelength spectral analysis to analyze the spectra fully consistently, which I have obtained before. In the case of eclipsing binaries and to conduct an orbital analysis, which yields valuable information about the masses of the individual stars, I used the physics of eclipsing binaries modeling software, which is called Phoebe. And after I obtained like the stellar and wind parameters of the post-interaction binaries, I wanted to know if we understand the properties of the stars that we are observing and what this means for our understanding of massive star evolution. So I also calculated stellar evolution models and binary evolution models with a MESA code. So Today I'm going to talk about 5 papers I have published or worked, collaborated with other people together over the last 3 years. So, but because I cannot explain you like each analysis in detail, I will use the binary AZB476 as an example to explain you how the analysis of this post-interaction binaries has been done and what we can learn from them. And then I will talk about the general picture of the results of the other papers I have obtained and what they imply for our understanding of massive star and binary physics at low metallicity. So why should we be interested in AZB476? The answer is it is an early O-type eclipsing binary. And this means that we have like an accurate determination of its period and inclination. And if we fit the radial velocities, we can also obtain reliable orbital masses. Furthermore, so on the left, I'm showing like a picture of this system in the optical, and you can see like the white dot over here is my star, and it is surrounded by this nice H2 region, which might be an indicator that it has like strong ionizing flux. So the spectral types of these stars in the binary are O4 subgiant plus an 09.5 main sequence star, which is rapidly rotating. If you now would do a similar mapping between the spectral type and the expected mass from the spectral type, you would expect that the primary has a high mass of 50 solar masses and the secondary has only 18 solar masses. But let's talk about the binary evolution. So to understand the binary evolution, we need at least a few input parameters like the current orbital period and the masses of the system, but also like temperature and luminosity. To obtain the period and the masses of the system, I have conducted an orbital analysis of the system and consistently fitted the light and radial velocity curve, which you can see on the left side over here. So from this fitting, I obtained that this binary had an orbital period of about 10 days. And also from the light curve analysis, you can obtain the light ratio in the considered luminosity band, so in the filter. And from this, I obtained that the secondary is way fainter than the primary. So the luminosity, the light ratio is 0.3 in the I band. And from the radial velocity fitting, I obtained that the two components have very similar masses. So the primary has 20 solar masses, so this is a factor of 2 lower what we expected from the spectral type, while the secondary has 18 solar masses, which is consistent. And expect if you have like 2 normal non-interacting stars, they have similar masses, they also should have similar luminosity, comparable temperature, and so on. But as we have like an extreme light ratio but equal masses, this is an indicator that this system has underwent a previous mass transfer phase, shedding off like the outer layers of the primary and leading to this low current mass of the primary star. So to obtain the luminosity, what typically is being done, and what I also did is like I conducted an SED fitting. So I modeled the spectrum of my system across like the entire wavelength range, which I'm observing. In the upper panel, I'm showing like on the x-axis the logarithmic wavelengths, and on the y-axis the normalized flux. And so in blue, you can see the observed spectra in the UV and in the optical. White open squares, and they denote like photometric marks. And the green dashed line is the synthetic spectrum of the secondary, which I calculated with power. And the black spectrum is so the black dashed line, dotted line, is the synthetic spectrum of the primary. And if you combine them, then you get the red line, which is like the combined synthetic spectrum of the binary. And you can see we can match the luminosity and the SED shape fairly well when we use like luminosities for the primary of 5.65 and for the secondary 4.71. This is also consistent with the light ratio in the I band, which we obtained from the light curve analysis. To obtain the temperatures of the stars, so you typically use like different ionization stages of the same element. The most prominent one, for example, is helium, which will help to obtain the temperature. So I'm showing in the lower part a spectrum, a normalized optical spectrum during a phase where I have like high radial velocity separation. So we can see the contributions from the different components in the spectrum. So you can see the black dashed line is a non-normalized, it is the normalized spectrum, but it's unweighted, so you can still see it in the plot. And so you can see it is contributing, it is a slowly rotating star, which leads to this narrow peak, while the secondary, the green dotted line, is a rapidly rotating star, which leads to like the broad shapes of the helium-2 and helium-1 lines over here. So this allowed me to pin down the temperatures of the components to be 42,000 Kelvin and 32,000 Kelvin. So now that I know like the fundamental stellar parameters and the orbital parameters of the system, I can plot my star in the Hertzsprung-Russell diagram and compare it with stellar evolution models. So I'm showing here a Hertzsprung-Russell diagram. So in the upper left, I'm showing the observed stellar properties of the Wolf-Rayet stars in the SMC. As cyan dots, I'm showing the OB-type stars. Then I have yellows and red supergiants in the SMC. And this magenta square is the position of the primary of the system of AZB476 and its position over there. Just as a reminder, the orbital mass of this primary is 20 solar masses, and the orbital period is 10 days. So as a first approach, you might say, okay, can I fit this track or can explain the observed stellar parameters of the system with a single star fit. So these stars should not have interacted. So indeed, a 45 solar mass track, single star track, would go through the position in the Hertzsprung-Russell diagram of this system, but it would predict that the current evolutionary mass is 43 solar masses, which is a factor of 2 higher than the observed orbital mass. So this means that single star evolution cannot explain the current observed parameters of the system. But of course, we are talking about binary systems. As I already have spoiled you, yeah, this might be a post-interaction binary. We can also calculate like stellar binary evolution models. And with this binary evolution models, I can actually well constrain the observed current mass of the system and the observed period of the system. So I'm overplotting this track, which you can see here, with dots which are equidistant time steps of 30,000 years. So which means if you see a lot of these black dots, then this is the phase where it is very likely to see my binary star. So if you pay close attention, then you will see that the position where I observe the primary star of my system, AZB476, in the Hertzsprung-Russell diagram, it is a region where my my binary evolution model actually predicts that this is a quick transition phase and that it is quasi impossible to observe the star. So either we were just really lucky that we just observed the star in this phase, in this transition phase towards the helium or Wolf-Rayet stars, or something is wrong with our physics. So as I said before, we already analyzed several post-interaction binaries in the SMC. So I extended now the Hertzsprung-Russell diagram to lower luminosities, and now I have added more magenta star symbols over here, which are the primaries of the post-interaction binaries we have analyzed over the last 2 years. And you can see something interesting already. All of them are located near the main sequence where you find this OB-type stars, which is roughly the position where you would expect to see AZB476. Sorry, I have to drink something. So if I overplot this now with primary models of binary evolution tracks, you can see that similar as for AZB476, these binary systems are predicted to be in a short transition phase, which is a bit strange because now it is not a unicorn anymore, what we have discovered, but we already discovered 4 stars of 1,000 known OB stars, which is a bit strange. So if you would trust the binary evolution calculations of the standard models, which I'm showing here, then you would expect to see in total 10 stars in this transition phase between the main sequence and this helium stars in this binary systems. But you would expect also to see like thousands of fully stripped helium stars. Recently, there have been a few been found, like I think it's 5 or 6, I'm not sure about the exact number, but it's way below 1,000. Of course, there are observational biases against this, but the sheer number of observations is also not speaking for the standard evolution models because we have more problems. As you can see, I color-coded these stars, so the primary models, in different magenta or pink colors. And these colors represent the observed surface hydrogen abundances. So if it has like a magenta color, it is a high surface abundances between 0.55 and 0.7 in mass fraction. And if it is like a pink square, then it is like a low surface hydrogen abundance between 40 and 30%. So I also overplotted now the binary evolution tracks with the surface hydrogen abundances. And as you can see, in this transition phase where our stars are associated with, this transition phases always have like low surface hydrogen abundances between 40 and 30%. And it's not like this is like an exclusive phase or a very short transition phase, but this high surface hydrogen abundances which we are observing are only associated with like the mass transfer phase itself. So which might mean that something is wrong with our models. Maybe it has to do something with mixing or mass loss rates or whatever, but clearly there's something off. So one of the least constrained mixing efficiencies is the mixing efficiency of semi-convective mixing. So which becomes most important after the main sequence and explains or it impacts the radial expansion of your star. So if you have a highly efficient semi-convective mixing, your star will expand less or slower, which means that if you are in a mass transfer phase, you will only transfer mass as long as your star is expanding. If you have now a star which is expanding less, this means it will also lose less mass during the mass transfer. And in the end, it will maintain a more hydrogen-rich envelope. So as you can see, the tracks for this high semi-convective mixing already have changed their shape and also their probability or the position in the Herschel-Russell diagram where it's likely to see the stars. So for the example, for the primary of AZB476, you can see that the model now predicts with this more higher semi-convective mixing that it is way more likely to actually find the star over here, so the primary star. While for the lower models, so for the lower mass models, the probability to detect the stars barely has changed. However, if we look at the surface properties of these stars, you can immediately see that these stars, as I already explained, they can maintain more of the hydrogen-rich envelope, which means they have higher surface hydrogen abundances, and also can stay at this lower temperatures. And this seems to be more or less in line with the observations we have seen or obtained so far. So you can see like this low surface hydrogen abundance of 2DSF163 is actually what you expect from stellar evolution models with more effective mixing and less radial expansion. And then there seems to be a transition, and suddenly for higher initial masses, you would expect that these stars lose less of their surface hydrogen-rich envelope. And this is the phase when semi-convective mixing becomes more important in the evolution of these stars. So this has severe implications for the evolution of the stars and also the final fate. So if you have like a primary star like this AZB476, and it doesn't evolve towards the Wolf-Rayet stars, it will end its life at lower temperatures. So, and it will spend its time at lower temperatures, which means it has less helium-2 ionizing flux. And also it maintains a large fraction of its hydrogen-rich envelope, which means in the end it will not explode as hydrogen-free supernova, but as a type 2 supernova with a hydrogen-rich envelope. So it has severe implications for our understanding of binary evolution at low metallicity. Okay. Enough about binary evolution itself. How do the wind properties of these partially stripped stars differ to the wind properties of like normal stars? So to study the wind properties of massive stars, you use the UV spectrum, where you can see like P Cygni profiles, which tell you important information about the mass loss rates of these stars. And also this is what we in the end see in the integrated spectra of redshift galaxies. So in blue, there's the observed STIS spectrum from HSD of AZB476. And in the red boxes, I'm showing the P Cygni profiles or the wind features that we use to constrain the mass loss rate of the stars. So I calculated my stellar atmosphere models, which are consistent with the optical fit. And again, you can see, so the green dotted line is the contribution of the secondary model, and 09.5 main sequence star at SMC metallicity is not expected to have or to show wind signatures. This is consistent with the other single stars of this spectral type. And this is also what we find. So it just contributes like to the UV flux, but not to the wind features. So, and the primary system, so the black, the primary star, so the black dotted line, and you can see that in the synthetic spectrum, we attribute all of the wind features to the star. So it is really powering a very strong stellar wind. And you can see in this absorption trough, the UV radiation of the secondary actually leads to a filling of the absorption trough, which is consistent with the observations. So this allowed me to obtain the stellar and wind parameters of the systems. And so the primary has a mass loss rate of -6.1, so, which means that it loses every 100,000 years 1 solar mass. So for its future evolution, this would mean that it will lose still like 3 to 5 solar masses, depending on the stellar evolution model which you are trusting in. So, okay, fine, but how does this now compare to other stars? So I made this figure a bit smaller because I'm showing down here the spectrum of NGC 346, SS, and 7. This is another O4 star in the SMC, which has very similar parameters. So this star has similar parameters to the spectrum of the primary of the AZU476. So you can see it has very similar luminosity, very similar temperature, but you can already spot it in the UV spectrum. The wind lines of this normal OB type star, they are way weaker. So the carbon 4 is not even close to being fully saturated. It's actually very weak. Nitrogen 5 is a bit more pronounced, yeah, and maybe a bit comparable to nitrogen 5 up here, but these lines are really fully saturated. They are strong and should be very prominent in an integrated spectrum. And this is also reflected in the mass loss rate. So you can see that the primary of AZU476, it has a mass loss rate which is 1 order of magnitude, so a factor of 10 stronger than the single O4 type star. So which leads to the conclusion that partially stripped stars and post-interaction binaries, they have increased mass loss rates and they have show stronger wind features in the UV, which is very important when talking about the integrated spectra of redshifted galaxies or galaxies in general. So how does this compare to the other partially stripped stars we have discovered? So I will not show you all of these individual spectra and make a one-to-one comparison, but I'm showing here the mass loss rates on the y-axis, and on the x-axis is the luminosity. And so the black dots down here, these are like main sequence stars from the SMC metallicity from different works, and the cyan stars are the Wolf-Rayet stars, and you can immediately see that these partially stripped stars, they seem to align with this Wolf-Rayet mass loss rates, and they have like 1 or even 2 orders of magnitude higher mass loss rates than the normal OB type stars with comparable luminosity and probably also comparable stellar temperatures, which is kind of crazy if you think about it, that it's 2 orders of magnitude stronger, and this is also reflected in their spectra. So talking about the spectra of high redshifted galaxies, so before I will talk about galaxies themselves, there's a very nice playground we can use, which are young clusters, because in these young clusters we can resolve the individual stars and understand their contribution to the integrated spectrum of the cluster. So in the SMC, there's a cluster which is called NGC346, which only has a young age of 3 million years, which means that most of the massive stars are actually just born and contains more than 20 O-type stars. So as the stars all have the same age, it is like an ideal laboratory to see how the different stars and also like post-interaction binaries contribute to the integrated spectrum. And So Matthew Rickard and we have studied and obtained UV spectra for the majority of the stars. So I'm showing here the normalized UV spectra sorted by their number, and you can also see their spectral type. I cutted this figure because there are way more to come with even weaker wind signatures. And you can see in these red boxes again, there are the wind features that we are interested in, which we see in the integrated spectrum of a galaxy. And so this is nitrogen 5, this is carbon 4, and you can already spot that SSN7 and SSN9 have really pronounced nitrogen 5 lines, which are very strong. And if you go down to lower spectral types, here's SSN13 again, yeah, they have like weak or even no wind features in their spectrum of nitrogen 5. And the same is true for carbon 4. So carbon 4 and SSN7 is really strongly pronounced. In SSN9, you can still see it, also well pronounced in half to saturation. And if you go to later types, here, for example, this 008 or 06 spectral type, the main sequence stars, you see that they barely show any carbon 4 wind features. So if you now look at the individual stars, so SSN7, as the spectral type already suggests, it is an binary system, and Matthew and we have shown that it's actually in the case A interacting binary, which is actively losing mass to its companion, and therefore it has been stripped and shows also, so the prime is contributing to this wind features prominently. So SSN9 already was marked as a binary candidate in the previous paper from Matthew and me. And so unfortunately also, or fortunately, these stars are the brightest stars. So SSN9 is the brightest star in this cluster, SSN7 is the second brightest system, and all of the other stars are way fainter than these two stars. So, which leads to the conclusion, if you have like an instantaneous starburst and let the age progress, that the most luminous stars are actually post-interaction binaries, and they also have like the strongest wind features, which means that the wind features and integrated spectra of distant galaxies are likely coming from the post-interaction binaries and possibly Wolf-Rayet stars, which have formed in the meantime. So this allows us now to do like a little thought experiment. So which stars are dominating the spectra of a galaxy? I'm showing here a Hertzsprung-Russell diagram where I created like synthetic populations. So if you assume like SMC metallicity and we have a starburst galaxy, like in the cluster we have an instantaneous starburst, and we have a high star formation rate and all stars have the same age, then you will see something like this. If you are at a very young age, so if you are at the age of 3 million years, like in NGC 346, then you would expect that most of the B-type stars are on the main sequence, and you have like the brightest stars are the post-interaction binaries or the partially stripped stars, and then you have like a few other OB-type stars. And in this synthetic population, you would expect that the UV flux itself and also the wind features are mainly coming from the post-interaction binaries. So if you let the time progress and let the stars evolve, then you will end up with the most massive stars dying, and after 20 million years, you will only have a few B-type stars, and then these stars start to wander off the main sequence, they expand, and also like more of these stars start to interact when they are in binaries. And after the binary interaction, what we have already seen in the binary evolution models I have shown before, after an interaction, the star actually gets more luminous, which means that the most luminous stars, again, in this population are the partially stripped stars and also some of the helium stars if they are not outshined by their companion. At least in the optical, because these are UV bright. So, which leads to the same conclusion as before. So the wind features from that we can see in an integrated spectrum should be actually coming from partially stripped stars, and they might be like the dominating source in these stellar populations. Of course, not all galaxies are starburst galaxies. You can also have just continuous star formation. And if you are continuously forming stars, yeah, you continuously produce partially stripped or fully stripped stars, you produce Wolf-Rayet stars, and you will end up with a population like in the SMC, and the number of the different populations go into an equilibrium value according to their lifetime. For example, if a star spends 90% of its life as an OB-type star and 10% as a Wolf-Rayet, then you would expect to see for 10 Wolf-Rayets 100 OB-type stars. And then we have a population like in the SMC, and actually the brightest stars in such a population are mostly the Wolf-Rayets and maybe some post-interaction binaries, but it is really dominated by the very massive stars and the Wolf-Rayet stars. And they are not only dominating the UV flux, but also the wind features that we can see in the integrated spectrum of a galaxy. So, as you have seen, I obtained and reduced multi-epoch, multi-wavelength spectra with the ESO VLT and the Hubble Space Telescope. And we have discovered using this data new OB-type post-interaction binaries in the SMC. And their spectral analysis has been conducted with the stellar atmosphere code POWER, yeah, which allows to consistently fit multi-wavelength spectra and to model the individual binary components and obtain their stellar and wind parameters. And these results are consistently modeled with the Phoebe software, which allows to obtain parameters from the orbital analysis, and the consistent analysis of the system reveals their true nature. And then I have computed binary evolution models, and I challenged the observations with the standard paradigm. And what I have found from these 5 post-interaction binaries is that these post-interaction binary products are actually not fully stripped, and it seems like there's something wrong with the standard assumption that a binary interaction leads to a full stripping of the star, which has severe implications for its final fate, but also for its feedback, as it produces less helium-2 ionizing flux, and you will end up with different types of supernova. And furthermore, I've shown that these binary stars, they have 10 to 100 times stronger winds than the OB-type stars, which are clearly dominating and contributing to the integrated spectra of high-redshift galaxies, which has severe implications for our understanding and interpretation of the new spectra we are obtaining with JWST. Thank you. I think I was really fast.
Okay, thank you very much, Daniel. It has been a very nice talk with many interesting results, something I didn't know. So it's great to hear directly from you. So now it's time for question. I have a couple, but let's allow people first, people in the audience to. So Alex.
Hi, Daniel. Very nice presentation. My question is about binary evolution, because I got a little bit lost. So when you have the tracks, can you listen to me?
Yeah, I can hear.
Perfect. Okay. So when you have the tracks, basically it's at the beginning is the classical single scenario of the main sequence, and just then when you expand towards the Hertzsprung gap, because of reaching some Roche law, I guess, they start the mass transfer. So 2 questions related with that is then first, why then you have this up in luminosity? And second, how do you determine which will be the mass of the secondary star? Because I guess maybe you constrain based on the observation, but I guess that the drop and up will be different depending on the mass of the secondary star.
Yes, so the evolution depends primarily actually only on the orbital period. And so the Rush law is defined as a function of orbital period and mass ratio, but the mass ratio dependency is very complex, and it is only a second order effect. But I still calculated both the primary and secondary in detail. And what happens, so if you have your binary interaction, so as you said, you're at the terminal H-main sequence, hydrogen is depleted in the core, you go to the Hertzsprung gap, your star starts expanding, and then it will hit its rush lobe and you will start transferring mass. And what happens is it drops out of equilibrium. Therefore, you can see this drop in luminosity. And as soon as it gains thermal equilibrium, it will start to increase in luminosity again. And the increase in luminosity, so why the star is brighter after the main sequence, is because it's now shell hydrogen burning, but you have less layers on top of it. So you have you're really looking into the deeper layers where most of the luminosity is coming from, which is not absorbed in the envelope. So this is why you have the increase in luminosity. And you can see this in MESA calculations fairly often. I think also in the bypass model, so in the stars code, you can see this effect happening also for different prescriptions of mass transfer.
Thank you.
Gloria?
Thank you. Good morning. I didn't realize my question was coming up so soon. Very nice talk and very nice overview. There is one pet peeve I have in talks when people are talking about binary evolution. And the problem is that the term binary evolution in the massive star community has become synonymous with mass transfer, as if there is no binary interaction prior to the mass transfer. And I think that is a very important problem that needs to be addressed, because if we do not contemplate the other processes that occur during the main sequence, then we're coming to wrong conclusions. For example, the binary interaction, quote unquote, binary interaction models that involve mass transfer and are used by everybody are assuming that the stars are in equilibrium. They're rotating, they're co-rotating, they're tidally locked, in other words, correct? This is not necessarily the case. In fact, it is not the case. There is a huge number of stars that are in eccentric orbits, and eccentric orbits are never tidally locked under no circumstances. And so I think we have to be very careful with our vocabulary, our words. If you go to lower mass stars, you have the heartbeat stars, and the heartbeat stars are clearly binary interactions, and they're not transferring mass necessarily, they're just pulsating. So that's my one pet peeve I have in general. It's not just with you, it's with everybody. Everybody uses the same term. So I just thought I should get it out there. And so then if you open up the possibility, if you open up the possibility to interactions during the main sequence, then other things are possible. Like, what is the mixing efficiency when you have an asynchronously binary star? Is this mixing efficiency large enough to produce more mixed stars and therefore lead to observations as the ones you are reporting? So I do think that this has to be kind of rediscussed. And so the question I have for you is, from your perspective, being a young researcher and having the ability to do all of these things, which I can no longer do, what would you think is the most important modification that would have to be made in codes like MESA to take into account these types of problems?
Oh, that's a really tough question. I think there are many construction zones. So, by the way, you are right about the binary interactions. It's a very wide term. It could also imply like tidal interactions, common envelope, and so on. So there are many possibilities to get there. And my proposed solution to this problem of the binary stars we are seeing might just be some overestimation. So it is just a parameter I turned, and then suddenly something came up. But the honest answer is there are so many uncertainties, like wind mass loss rates, like what are the mass loss rates of this post-interaction stars in a transition phase or in the end, which have a severe implication on the orbital evolution, as well as like the stellar parameters of these stars. Binary interactions or mass transfer itself is also not very well understood. As you said, there are several post-interaction binaries which show eccentric orbits, including AZB476. By the way, it has a low eccentricity, and something which might be the case is that you lose some material through the L2 or L3 point and form a circumbinary disk, which could lead to an eccentricity enhancement. So am I still here? Okay, yeah, because I didn't see anything moving when the green frame was gone. Yeah. There are many things. I think the uncertainties in mass transfer physics themselves are like the biggest construction zone. So, but also using like mass loss rates can have a severe implication on your interpretation of your results. So if you are using wrong mass loss rates for your evolution, then you could fully be misinterpreting like the results you have in the end. I hope this answered your question. It was a very long one.
Yes, thank you.
And not
Thank
the
you.
precise one.
Okay, any other question coming? If not, I can ask a question myself. So it's very interesting and has sense everything you've said about the donors and how they evolve. But then probably in purpose, you have not mentioned the gainers. And if I understand correctly, the gainers will also appear as rejuvenated, more massive stars. So it's going to, they will be also populating the same region of these stars you are mentioning. So how you distinguish one from the other, and what can be the impact of the gainers, or the, how to say, the importance of the gainers in all these games you're playing with the interpretation of the populations?
Very good question. So I have not talked about the gainers. In this case, I'm showing only case B system, or I have only so far talked about the case B systems. And all of these stars have companions which are rapidly rotating or even BE type stars. So these low ones have BE type companions. This one has a rapidly rotating companion star. And what I'm using to model, or how we interpret this, is that during mass transfer, you are also transferring angular momentum. And as you accrete the material, your secondary will start spinning up. And you can only accrete as much material as long as you are below critical rotation. And in this case, B systems with wide orbital periods, tides are not very efficient, and therefore you don't have like any mechanism spinning down these stars. So they don't get rejuvenated, is the essential thing. They just get like spun up. At least the envelope got spun up. The core doesn't, or over time maybe. But so they will behave similarly to the normal primary stars if they would initiate a reverse mass transfer on a later compact object. But in the case of case A systems, I have also a nice paper on this stuff, but I didn't include it in the talk. So if you have a case A mass transfer system, then you have like a very efficient mass transfer because your stars can get tidally locked. You have an efficient spin down, so you can transfer all the mass which is lost from the primary to the secondary. And what I can see from my models is that these stars, the envelope gets more rejuvenated than the core. So they have like a different envelope to core ratio. And if these stars would initiate also a mass transfer phase, their orbital, so their radial response is different because they already form like an intermediate convection zone, or during the main sequence, they're expanding less. And you can actually see that these systems, especially in the high mass regime, instead of getting fully stripped, they get only partially stripped and appear as like cool Wolf-Rayet stars instead of like fully stripped normal Wolf-Rayet stars. And they have different chemical signatures. For example, they have like not fully CNO equilibrium abundances because you go into this intermediate convection zone where you have something like between CN and CNO equilibrium abundances. So this would be one possibility to differentiate between a partially stripped star in a binary system with two active stars and one which has like gained mass and has an unseen companion.
Okay, fully clear. So thank you very much for your explanation, because I could follow you perfectly. Thank you.
Perfect. I'm surprised. Also a very long one.
Any other question? Okay, if not, we always have time afterwards to ask Daniel. The talk will be in YouTube, so you can see it again, and if you have any further question, or you have already maybe now, but you prefer to ask him directly, I'm sure he will be happy to answer you. So then let's thank Daniel again, and yeah, it was a pleasure. Has been a pleasure to listen to your science. Thank you very much.